Hi
Hi
everyone,
everyone,
welcome to our
welcome to
series of
our series of
seminars.
seminars.
Today we'll be
Today we'll
receiving
be
Miguel
receiving
Felipe
Miguel
Silva
Felipe Silva
Vasconcelos.
Vasconcelos.
He will be talking to us about towards greener multi-clouds. This work is being developed as his part of his PhD uh, under advisement of Daniel Cordeiro and Fanny do Fussé. So Miguel, thank you for accepting our invitation. You may start whenever you're ready. Thanks.
So, Hello everyone. I said I'm Miguel, and today I'm going to talk about a little about what I'm have been doing in my PhD. So let's start. We all know that cloud computing was a revolution for the industry and academy because of its capacity of providing large amount of computing resources on demand. And here I have a picture of the modern cloud infrastructure. We see that the data centers are all distributed around the world. And this geographically distributed, it's called in the literature as multi-clouds. And the reasons for this distribution are many. For example, to reduce the latency for the users, to meet the demand of the users also, and finally, for example, for availability reasons. If one region goes down, other regions can receive the request, for example.
Miguel, just a comment. Sorry to for interrupting. Your microphone is bumping against your clothing, so it's making some noises.
Okay.
Thanks.
And the problem is that the cloud is really energy intensive. As you see, nowadays, the data centers already consume 1% of the global power. So it's already more than some countries. And for the future, uh, a lot of estimations predict that the scenario will be even worse, as you can see in this figure. And most of this energy came from non-renewable sources. As example of the data center alley, it's a region in the northern Virginia in the United States that has a lot of data centers. And in 2019, it handled 70% of the internet data traffic, but it was only supplied by 2% of renewable energy. And here is a picture of a screenshot of this electricity map service. In the service, you can see in real time how green, so how much renewable is your energy. And here is the location of Virginia in the data center alley. And the major cloud players are already started developing or already deployed some solutions to try to adopt a renewable energy. And one example also is the from Amazon. You can see how much emissions your applications is producing to the environment. So here's an example from the Amazon EC2 and all the other services from Amazon. And here, one question that remains is which renewable could we use? So hydroelectric dams are not so feasible to include into the data center, and also offshore windmills because they are in the ocean. So it's wind power from uh, wind turbines in the ocean, so they are not appropriate to install in a data center. And about eolic power, the wind speed is a little hard to predict, and the solar is the easier to predict because it follows daily and yearly patterns. And also here's other screenshot for the electricity map. You can also see the solar irradiation intensity around the globe. And about solar power, the cost of solar power is really decreasing in the last years. So now is the for new electricity power plants is one of the cheapest in comparison with all the others, and it's expected that this cost will keep decreasing. But one of the main problems with renewable energy is their intermittency. So it's variable nature because it depends on a lot of factors. For example, on time, the weather, the geographic position of the data center, and the seasons of the years. So here again, the figure about the solar irradiation, we can see that in this moment would be appropriate to solar power would be produced in this region, but in this other region, no solar power would be produced. And what is this follow the renewable approach? So the virtualization is a key aspect of cloud computing because it allows to create virtual resources from a physical server and run more services and applications using the same hardware. And this live migration is a capacity that you can transfer these virtual resources to other servers without interruption. And this part without interruption, it's why it's called live migrations. And so this follow the renewables approach, as the name says, it's try to migrate or allocate the workloads to the data centers that have more renewable power available at the time. So here, for example, in this figure, if in this moment the follow the renewable approach would migrate the workload to these regions that have more renewable power available. But follow the renewables also have costs. They are not for free. And one of the major costs is in terms of the network usage, because you are migrating the workload to other data centers. So there are two types of impact in the caused by the live migrations. The first one is the energy consumption of the network device themselves, because you are using the network device. And the second one is the impact caused by migrating the workload, because when you migrate the workload, there's also extra computation that occurs inside both the source and destination servers. And in the first study, we analyzed this indirect impact in terms of the network congestion and the energy consumption that's generated from these live migrations in the follow the renewables approach. So now I'll talk about the solution that the algorithm that we developed. So it was based on a previous work called Nemesis that uses a centralized controller to handle the workloads, uses stochastic prediction for the green and brown power, and uses grid heuristics for the scheduling, because in clouds, the workload size can be huge and we need to take a fast decision. Follow the renewables strategy for both the initial workload allocation and the migration between the different data centers, and server consolidation to reduce the number of servers that are being used. So here, just a visual representation of this framework. So here we have data centers distributed around the country, and we consider that they are supplied by solar panels to produce solar energy and use as backup the local electricity grid. And here is where the Nemesis would be inserted. So it receives the workload and schedules them to the different data centers. And this it was a basis from my first work. I explained briefly the 4 steps of the algorithm. So the first step is the pre-allocation of the incoming workload. So it tries to find the server that is expected to consume the least brown energy, and here it uses the stochastic prediction and also grid heuristics. And since it uses grid heuristics, it needs, in the second step, it reviews these previous decisions, trying to find a better solution. And the third step, it performs migrations between the different data centers. So it's called inter-DC migrations. So we try to migrate from the data center that's consuming more brown energy to the data center that have more green energy. And we considered some restrictions. For example, the migration needs to finish during the considered time slot. The virtual machine will not finish execution during the migration, otherwise we only waste energy. One data center could only migrate to other 2 data centers, and one migration for one DC are planned one after another. So these last 2 restrictions were to try to avoid a little of network congestion. And the last step is the server consolidation, where we perform intra-DC migrations, so migrations inside the same data center, to try to minimize the servers that are turned on. Now about the extension of the work that's more focused on the congestion and the network consumption is the C Nemesis, and it's focused on the last 2 steps of the algorithm, so the migration of the running VMs and the server consolidation. And the main modifications are, now for the migration planning, we take into account the full topology of the network. So we take into account the bandwidth of the link and the history of its usage, so when the link is used. So we can, since we are considering we take into account the topology, we can validate which link is used or not, so we can perform migrations in parallel. We can also perform distributed in time interrupt DC migration. And since the migration planning is using the full topology, the precision of the duration for the migration. So we also use an algorithm to predict how long the migration will take. When you take into account the full topology, the precision of this prediction is increased. So it's really precise. And now about some experiments that we did. We used the SynGrid framework because it's a well-validated framework by the scientific community, over 20 years of usage. SynGrid also models the power consumption of the servers, and it uses a linear model, so it's fast, and some studies also proves that this linear model has a really good precision. And for the network, it uses flow-level TCP modeling. Some simulators use packets, are simulate the distribution of packets, but for the packets, it takes a long time to simulate. So it's not the precision using packets, simulating the packet transmission is higher, but it do not scale for a cloud. And SynGrid using this flow level has a good precision and it scales, and we can simulate in a reasonable amount of time. And for the migrations, to model the energy consumption, we need to make a little modification in SynGrid to use one CPU core in the host that we receive the VM. It will execute one task to simulate this live migration during the migration process. So for the cloud platform, it's based on a real infrastructure, the Grid 5K, and we considered 1,035 servers. They were distributed among 9 data centers, and the servers are considered homogeneous in terms of CPU and RAM. And for the network, we consider that the servers are interconnected inside the same data centers by 1 gigabit network link, and between the different data centers with 10 gigabits network links. And here we have the cloud topology. We can see that some links are shared by many data centers. So if not plan with caution the migrations, we could have a lot of network congestion. And for the input for the solar power production, they were based on real photovoltaic production data from the University of Nantes, so collected the power production for 1 week. And to simulate the different locations, we used different weeks in the year. And you can see that every location has a little different power production profile. And about the workload that we executed, we considered virtual machines, and we used samples from traces of real cloud providers. So we used the traces from Google and from Azure. And what we extracted were the submission time when the virtual machine was submitted, how much cores each request had, and how long this virtual machines executed. And for the run, we considered 2 gigabytes per requested CPU core, inspired in the T2.small instance of Amazon EC2. And we did not model the network usage because these traces do not provide the network usage. So in this work, the network usage is only by migrating the virtual machines between the different data centers. And here we have the characteristics of the workloads. So in purple is the CPU cores demands of the running virtual machines, and yellow is the submission of the virtual machines. We see that we have 2 different workloads, behaviors. So from the Google workload, it keep increasing throughout the week. And for the Azure workload, in the beginning, we had a peak of submissions, and then after it became almost constant, the number of submissions. And now a little about the results of these experiments. So I will present the results in terms of the analysis of the live migrations performed, both in terms of network congestion and the wasted energy, the total and brown energy consumption, and a comparison with 2 other works from the state of the art. So the first work from the state of the art is this WSNB, workload shifting non-brownout. So this work, it only performs only uses the follow the renewables strategy for the initial allocation of the workload. So it do not perform live migrations for throughout the execution of the workloads, only for the initial allocation. And it do not shut down the underutilized servers, so there is no server consolidation. And the second baseline was the follow me at source. So this uses the follow the renewable strategy both for the initial allocation of the workload and migrating the workload during its execution. And for the migration, it has 2 sub divisions. So it either only perform migrations inside the same data center or within different data centers. It has server consolidation, so the underutilized server are shut down. However, it do not consider the network for the planning of the migrations. And just a remark of the adoption of the follow the renewables. So the WSNB and the follow me attest inter only applies the follow the renewables for the initial workload allocation, and the others algorithms perform like use follow the renewable strategy for the whole execution of the workload, both the initial allocation and migrates to different data centers when the green power production availability changes. And to evaluate the network congestion, we compare it with a perfect scenario. That is, all the migrations were executed again individually, but now they have full access to network resources. So in this scenario, it's impossible to have network congestion. The virtual machine, when it's migrated, will have full access to the network. And the network congestion will be in the term of the additional time the migration takes when planned by the previous scheduling algorithms in comparison to this perfect scenario. So here, just to make it easier to visualize what was happening in terms of the network congestion, I have these visualizations. So for here, it says that a link would be under congestion during a time slot if a migration took more than 10% compared to the perfect scenario. So in this figure, I have the network topology. So the endpoints are the servers among the data centers, and the lines are the network links. In yellow, it means that during this time slot from midnight 15 to midnight 10 to midnight 15, no congestion happened in this link. And in purple, it means that during this time slot, these links were under congestion during some specific moments in this time slot. Oops, the video. So can you see the video?
Yes.
Okay, so here's the evaluation of the algorithms. We can see that our proposed solution that takes into account the full network topology basically didn't provide network congestion. The previous algorithm where CNAMES is based, it had some network congestion because it uses a more simple migration planning algorithm. And this other baseline, the follow me since it do not consider the network at all, it has congestion basically almost the entire week. And you can see also that the version that migrates the virtual machine between the different data centers had basically more congestion than the one that perform migrations only inside the data centers. And for this one, it only had congestion during one of the time slots that just passed. And now I have more detailed information about the network congestion. So here I'm evaluating in terms of the total seconds that here I'm evaluating in comparison of the perfect scenario, how long it takes to migrate. So for example, here in the average, the Nemesis algorithm, in average, it takes 1.6 times more to migrate than the perfect scenario for all its migrations. And in the maximum scenario, the maximum case, it took almost 4 times more to migrate than in the perfect scenario. For the Nemesis, as we saw in the previous video, basically that no congestion during the simulated week. And in the maximum, it was 1.32 of the compared to the perfect scenario. And for the baselines, we see that since they do not take into account the network, the migration is really higher than the perfect scenario. So for the follow me intra, in average, it took 4 times more, and in the maximum, it was 25 times more. And for the inter, it's 8 times more in average, and more than 100 times more in the maximum scenario. And using this information of the total extra seconds that it expanded migrating in comparison to the perfect scenario, we can estimate the power consumption of these migrations, the extra power consumption. I say wasted here, I mean wasted because this energy was in addition to the perfect scenario. So for the Nemesis, the algorithm that we proposed, to see that the power consumption, the wasted energy was really low, so tens of watt hours, so almost nothing. For the Nemesis algorithm, it was a little higher, so hundreds of watt hours. And for the baselines, we see that the power consumption is really high, is in hundreds of kilowatt hours. And this power consumption could even power the cloud infrastructure, for example. Here, for the case of the Google workload, one of the algorithms wasted around 300 kilowatt hours. And this energy could even power one of the data centers for approximately 44 hours. And at maximum capacity, I mean, using all the cores of all the 38 servers. And in terms of the total and raw energy consumption, we see that the Nemesis, it consumed a little more energy than Nemesis because it performed more live migrations, but it reduced a little the raw energy consumption because it migrated to the data centers that had more green energy. And for the follow me intra, we also see that the version that perform migrations to the different data centers had a lower energy brown energy consumption. And finally, the WSNB algorithm, the one that do not take into account, do not perform live migrations to different data centers, have the highest brown energy consumption, and also the highest total energy consumption because it do not shut down the servers that are not that are idle, not perform server consolidation. So this was for the first experiment in terms of the follow the renewables. Now I'll talk a little about the first experiments that we did on the dimensioning. So as I said before, intermittency is one of the problem. So one possible solution is to store this renewable energy in the energy storage device. And in this work, we are considering the lithium-ion batteries because they have the highest cost benefits, both in terms of the capacity of power density. And this density is really important to the data center because it's how much space the battery would take. And the question of space is really important to the data center because you could also include more servers or more cooling devices instead of a battery. And the self-discharge of the battery is really low, so 0.1% to 0.5% per day. And they also have a maximum depth of discharge of around 80%. So this is basically how much you can discharge the battery without reducing its lifetime. So if you discharge the battery completely from 100 to 0, the lifetime of the battery will be decreased. And it also has a high efficiency. So the charge efficiency is around 85%. And in the last years, the price of the batteries is also going down, and it's also expected to become even lower in the next years, also because of the uh, popularity of the electric vehicles. They are becoming more popular, so it's expected that the price of the lithium-ion batteries will continue to go down. So now we are exploring these lithium-ion batteries from the short-term storage, and we use to follow the renewables instead of long-term energy storage devices. And in these first experiments, we considered green energy traces from different regions of the world, the adoption of lithium-ion batteries, and also to has the same cloud infrastructure and workload that I showed before. So based on the Grid 5K and the workload traces from the Azure and from the Google. So for the new green energy traces, they were estimated based on the solar irradiation data. So here I have the 9 new locations. So you can see that they can complement each other throughout the year. And so for the first estimation of the size of the PV panels, it was a simple estimation. So I take the power that the data center consumes during 1 week, and I also take into account the power that one square meter of PV produces during 1 week, and I divided one by another. So for example, in Canberra, Australia, the maximum power consumption of the data center was 4.2 megawatts hours, and the maximum power production by one square meter PV was 26 kilowatt hours. So for this week, it would be computed. It was computed that it needed 164 server PVs. And here I have the power production for the PVs during the whole cloud. We can see that during the entire week, in all the data centers, that there was some point in time that has green power production. So there's no point that there's zero power production during this simulated week. So here's just to make the map of the previous location and the new locations. So the data centers are sorted, these new locations are sorted based on the solar power production that each location can produce. So the data centers that have the highest number of servers were the ones where the solar power production was higher. And for the batteries, we take in our simulations account the carbon footprint for the entire life cycle. So for the production to discarding this battery, we also take into account the 80% of depth of discharge. So you cannot discharge the battery completely. Discharge and discharge efficiency of 85%. And for the capacity, for this first experiment, we take into account that the capacity of the battery was enough to supply the data center during 12 hours. So, for example, during the night. And we didn't take into account the self-discharge because it's really low, so 0.1% to 0.5% of charge per day. Okay, so here is the comparison of the energy consumption. First, without the batteries, just using this new power production balance, these new green energy traces. So for the brown, and we see here that we produced a lot more green energy, and we reduced the brown energy consumption. However, we used less green power in comparison to the scenario where the data centers were only inside a country. And when we include the batteries, we increased this green energy usage, and as a consequence, we also reduce the brown energy consumption of the data centers of our multi-cloud. Okay. In terms of the carbon footprint, we also here take into account the emissions of using the local electricity grid in all the locations of the data centers. And we also found some data about the carbon emissions of using a PV panel and using power from the lithium-ion batteries. So in terms of carbon emissions of the cloud, so if you only use the electricity from the grid, we have 16 tons. If you use PV and the energy from the grid, we reduce it almost by 2 from the first case. And if we consider PV, grid, and batteries, we reduce it basically by a factor of 3, the carbon emission of the clouds. And finally, I'll talk about some more the ongoing work that I'm doing in the dimensioning problem. So as I showed before, each region has a different carbon footprint for using the grid, but also each region has a different power production potential, a solar power production potential. For example, Paris already has a green electricity grid, has a low emissions because it uses, in France, there's a lot of nuclear power. However, the solar power is not really feasible in France because they don't receive a lot of irradiation throughout a year. So here's how much energy one PV square meter can produce during 1 year. But in contrast, regions as Johannesburg, that has the highest carbon footprint, is the one with the highest solar power potential. So for Johannesburg, it's interesting to have solar panels. So the objective is to minimize the carbon emissions of the multi-cloud, considering that the data centers are geographically distributed. They have solar panels to produce photovoltaic power, lithium-ion batteries for storing the renewable energy, and the grid is used as backup power. So in this ongoing work, to solve this, we are modeling and solving it using linear programming. So we modeled it using PUP. So PUP is a Python library that is really easy to model your linear program. And you export this linear program to be solved in an efficient solver, for example, as Gurobi. And for this work, we are doing it in collaboration with the Data Zero project. And in the Data Zero project, they are exploring one data center that's only supplied by renewable energy. So that is, there is no backup power from the grid. and they use like batteries and also a long-term energy storage device. So just to remember what is a linear program. So linear program is the mathematical problem of optimizing a linear function. So for example, the optimization could be minimization of a linear function. So here is just minimize x1 plus x2. And here is the objective of the linear programming. X1 and X2 are the variables of this linear program, and the relations between these variables are called the restrictions. So here I have the restriction of the linear program. And one interesting characteristic of linear program is that if you use only linear real variables, there is a algorithm that can solve it in a polynomial time. So it can solve it in a reasonable amount of time. And for our scenario, what the variables of the algorithm that the solver will try to play to find the optimal solution is the workload. So the solver can define how much workload will be executed in any of the data centers, how much is the capacity of the battery in kilowatt hours, the size of the PV panels, how much power can be discharged and charged in the battery at each time slot and at each data center. So just to show some restriction of the LP, this first restriction is about the power consumption and production of the data center. So PdK is the power consumption of the data center D at the time K. So this power consumption can be supplied by the green power, the power produced from the solar panels, and it can also be supplied by the batteries, so the power that is discharged from the batteries. And if there's not enough power, both of these solar power production and the batteries to supply the data center, we can also use power from the grid. And if there is some power that remains from the solar power production, it can also be charged in the batteries. And the second restriction is about the batteries. So the BDK is the level of energy in the battery. So it's how much energy there is in the battery. So it depends on the energy in the previous time slot, in addition of what is charged and discharged in the battery at the time slot. And this eta is the efficiency of the charging and discharging process. And this other restriction is just to enforce the maximum level of charge of the maximum depth of discharge of the battery. So you cannot discharge the battery under 20%. So BAT is the size of the battery. And the battery cannot go higher than 0.8 because after 0.8, it's not do not have a linear behavior. And the objective of the LP was to minimize the emissions. So here is the emissions from the grid. So how much electricity we use it from the grid, in addition to the emissions from manufacturing the PVs and manufacturing the battery at each of the data centers. So for the inputs of the linear programming, we considered 1 year of operation, and the workload was based on the Google traces. We used real world data from the carbon emissions and solar irradiation traces from MEHA 2. We considered the data centers 9 data centers with homogeneous servers in terms of CPU and memory. It's the tower servers is the same server that I showed before. And for the network topology, it was considered a fast tree network topology because it's one of the most common in the cloud data centers. And in this network topology, we can know how much network switch we need to match the size of the servers. So you can compute how much was the power consumption of this network topology also. And the power usage effectiveness was 1.2. So the power usage effectiveness is calculated in this way. So it's the total power consumption of the data center divided by the server's power consumption. So it also takes into account the cost for cooling. For the photovoltaic panels, we consider 250 kilograms of CO2 equivalent per square meters, and the efficiency to convert the solar irradiation to power in watts is 0.15, and the lifetime is 30 years. For the lithium-ion batteries, it takes 59 kilograms per each kilowatt hours of capacity. The charge and charge efficiency is 85%, and there's no self-discharge, and a lifetime of 10 years. And what we are interested is the size of the solar panels and the capacity of the batteries. Okay, so for the results, in comparison to the scenario without PVs and batteries, the cloud emissions was reduced by a factor of 6. And in terms of the size of the batteries, we first see that for Paris, makes no sense to use batteries because the grid is already really low emission, low carbon intensive. And for São Paulo, so here in Brazil, we also have hydroelectric power that is low carbon intensive, so that's why it's also had a small battery. But for the other data centers, the size of the battery did not vary that much. And for the PVs, again, Paris had a really small PV, and São Paulo also are the ones who have the smaller PVs. And also interest for the size of the PV panels because CO in Singapore is the one that has the highest size of the PV panels. And one of the motives is because, one of the reasons because in CO, the potential for generating the solar power is not that high. So you need a more PV area to generate the same amount of power. For example, as Dubai and Johannesburg that are the ones that have the greenest, they have the highest potential for producing solar power. In terms of the power consumption, so in green is the how much power was produced from the solar panels. In blue is the power consumption of the data center, and red is the power from the grid. We see here that the solar power production was really high, so even we charged in the battery, so there was overproduction of the solar panels. Okay. And here is the distribution of the energy that was used to supply the data center. For example, in each day, so the batteries are taking into account basically half of the data center daily energy consumption. So basically for night computations, the other half in Canberra was from the power from the solar panels, and the red is how much power it used from the grid. And finally, in here, I have the level of amplitude of the battery. Basically, it's how much energy used from the battery in each day. So here, the maximum is, so you discharge the battery completely during these days, and after use it less. So for Canberra, the battery was only used at fully in the first 2 months, basically. During 2 months, not the first, because here they are sorted by in decreasing order. In some data centers, for example, as Johannesburg, there's no power from the grid, and the battery was used completely longer than the scenario of Canberra. And for Dubai is the one that has the highest usage of the batteries and also no power usage from the grid. And for São Paulo is there's a little more variation of what is the usage because the electricity grid of São Paulo is already really green. So it uses really low energy from the batteries, a lot of energy from the grid, and also a little bit of energy from the solar panels. And even if the batteries are small, they were used more than half of the year. And for Paris, since it has no batteries, so it used basically power from the grid almost all the time and only a little of the solar panels. Okay, so as future work, so okay, the solver computed the maximum value the optimal volume for the dimensions, but we need to explain why is this the optimal value? When is viable to use solar panels and batteries? And also this was an offline optimization problem. How do we take into account also the online scenario, take into account, for example, the network congestion for the migration planning, and take into account this new scenario of the clouds are geographically distributed, the latency is really higher than before. So the migrations are, as a consequence, really higher. So the latency is the bottleneck for this live migration between these different data centers. So before, considered only a country, the maximum was around 2 minutes to migrate a virtual machine with 12 gigabytes of RAM. And now, considering multi-clouds all around the world, the minimum is around twice than the maximum as before, and the average is 14 minutes. And the maximum scenario is almost 1 hour just to migrate a virtual machine. So we have to take into account also some quality of service constraints to see which workload can be migrated. Maybe only a batch of tasks could be migrated, given this higher latency that could be a problem for some applications like services. Okay, so that was it. Here is the funding that I received, both from LabX Percival Lab and also from FAPESP. So thank you for the invitation. And here I have a link for the material of the first part of the presentation. That was the paper that we published in the Smart Greens. And I will be glad to answer any doubts that you have. That's it.
Thanks, Miguel, for our presentation. Questions?
Yes, I have a question. Could you come back to the map where you put this one? So this is from Azure. This is the data center of Microsoft.
Yeah. So here.
So they only have one region in the US.
Here I just selected some of them.
Okay.
It's just for illustration purpose, just to, for example, to show the value of the latency that's now is really high between the different regions.
Yeah, this map is more about the link between the continents than the data center by themselves. Okay.
Yep.
Nice.
It's more
okay.
So the high latency between these regions.
A comment about Paris and France. You were saying that the electricity was really green and not producing any carbon footprint because of the nuclear plant, actually. Yeah. But the thing is, maybe you should put some battery at the moment, because I think half of the nuclear plant are not working anymore because they have problems. So France is very in a big energy crisis right now, and I think it probably would be a good idea to have those data centers only using green energy. Mm. But I think it was really a good, an interesting point to consider the carbon footprint of the production of the brown energy. Because at the beginning, when you show the brown energy, I was like, yeah, but it's not always that brown.
Yep.
Because it really depends on how you produce the energy. So I think it was very nice. So actually, it already answered one of the questions I had.
Yep. Anyway. At this point of the carbon footprint, so this was the optimal computed by the solver, because at the time that I extracted, so it was the carbon footprint from last year in Paris. So it was around 52 grams of CO2 per kilowatt hour. So maybe in this year, as you said, many nuclear plants were shut down, so this value will be higher. So considering this higher value, probably we'll computed some PVs and batteries for Paris.
And probably there is variation in this value of memory of carbon footprint, because for example, in Brazil, at some point we have this hydric crisis, and they had to power on some coal factory and stuff like this. So do you consider this, or is this a variable, or is this something constant for you?
This was a average of the year. This
okay,
but the service electricity map, so it's starting to provide like a time series of the carbon intensity over the time. So after we can also take into account this variation.
okay, nice.
It's really recent, this function to provide the carbon intensity over time.
Nice, very interesting. Thank you, Miguel.
More questions? Well, I have some.
one.
Go ahead, Sandra.
Thank you. Thank you, Miguel, for the presentation. Very interesting work. I'm curious about the state of the current frameworks and tools that people use in the data centers. Because I had the experience of doing some research on green data centers a few years ago, like, I don't know, 7 years ago, 10 to 7 years ago. And you mentioned that you use the simulator to do your work, right? So you put your algorithm and heuristics and etc. all inside the SimGrid, right?
Actually,
did I get it right?
Yeah, I use it as SimGrid. Yep.
Yeah. So back then, I tried to look into like Apache Mesos and stuff that people use to provide resources in a data center, and those thinking about putting some intelligence for resource managers towards a better energy consumption, but it would not be easy to do it at the time because the tools were very not prepared for being customized, let's say in this way. And do you see people from those frameworks like Apache Mesos or anything else, OpenStack, the stuff that people use to provide cloud and data centers, do you see real movement of those developers trying to incorporate stuff that people in research do on simulators, etc., for better resource utilization towards better energy consumption in the real tools, or this is still only available because, I don't know, Amazon has a lot of PhDs working for them, so they can do their own customization, and Google and Microsoft probably, but we as researchers, if we take a look into these tools, it would be like impossible to do anything inside them, and we still need to only take our work inside simulators to be able to try to convince people to do better work on energy. What's your take on this? Did you see anything published that, I don't know, indicates that those tools are like it's feasible to try to do something then nowadays?
Yeah, like I believe that to be like a pressure, because since the major cloud providers are made commitments and are already deploying, so probably all the others will also incorporate. But as, for example, as a public available tool that already take into account this power consumption, like for example, green energy, I don't know yet. Some that is publicly available.
Okay. I'm not saying that you need to do that, by the way. You need to do your thesis. That's not what I'm saying, because I tried that at that time, like I said, 7 years ago, and it was like impossible. I had 1 year to do a research project, and in 1 year I wouldn't be able to do anything inside those tools. They are too big and too intricate. So, but I was wondering, because it would be very nice if the people developing those frameworks start doing something that would be easier for researchers to like try to do some real simulations in machines to understand what would happen in like even in a micro data center. Of course, we would be able to do in a big data center, because we don't have big data centers to experiment with. But even in an in-house cluster, would be nice to see what would do. What would it take to try to do this in those frameworks? Because I think that's what Amazon and Google and etc. are trying to do inside in-house, but they have like an army of programmers to do that. Okay, thanks. This was just this curiosity. Thanks for the presentation, and congratulations for the work.
Any more questions?
I have one question, just out of curiosity. At some point, my connection dropped, so I'm sorry if this was already addressed. But when you mentioned using batteries to store energy, the production of those batteries, does it have a carbon footprint by itself? Is it renewable?
Yep. So we take it account. We take this into account. So it costs 59 kilograms of CO2 per kilowatt hour. So the capacity of the batteries also take it account.
Okay, that's the production of the batteries themselves. Yep. Okay. Thank you.
And I have just one more question about the graphs you showed in page 82 or 85, for instance. You passed by them too quickly. I didn't really understand what you're showing them.
So, for example, here,
is
one is the energy consumption of the data center in a day. So the total energy consumption of a data center. So, for example, in Dubai, half of the energy consumption is basically from the batteries, and the other half is from the PV. So here is the source of the energy that supplied the data center, and how much that source has supplied the data center.
Okay, understand now. Well, what I was wondering is, why do these bands show up? Are the days of the week, the beginning of the months? What are those?
Maybe what's something of the,
or is it some artifact of the way it's being drawn? Maybe.
Yeah, maybe when compressed it.
Okay. And another question: do you consider lag for when you're considering the migrations? Because sometimes people are willing to pay more, not even in terms of green energy, but in terms of energy, to place their loads near the users. So when you are considering the migrations between data centers, do you consider the proximity of these loads to their users as well, or not?
No, but for example, in this scenario, if the geographically distributed clouds, because before we were considering all of the multi-clouds inside a country, so inside of France. But probably now we need to take into account these more restrictive constraints for the placement, because the latency is really higher, and it probably will affect the quality for the clients. So for first moment in the previous work, we didn't take into account the network congestion. No, we take into account network congestion, the location, because it was in outside the country, so and the latency was not that higher inside this network topology.
Okay, thank you. Do you have more questions? I guess not. So thank you again, Miguel. Let's thank Miguel again for his presentation. And you're all very welcome to come to see our next seminars as well. Thanks.